again, lining up that slit with the light right there. So just grab one. Which way do you hold it? You're holding it like that way is fine, or turn it upside down. I can't remember. The numbers might be upside down. And you can get closer if you need to get it lined up, you can get like that.
What is that called, the whole contraption?
I want to say spectrograph. Spectroscope. Quantitative spectroscope. Are you seeing the colors?
Yeah.
What numbers? Can you see the numbers?
Kind of. I see a very sharp one on 670, I think.
Okay. I assume that's red.
Yes. There's a sharper one on 550. There's green. And then there's like a kind of dim one on 500.
That was bluish. And more than one can do it at a time. So just should be enough for everyone. You see the color lines? You look through there and you want to line up this slit. There's a slit right here. You line that slit up with the light. I assume you saw it.
Yeah.
All right. We'll, at some point, go to the computer and look up those numbers, assuming Patrick saw correctly, and that should come up with a unique identification for what gas that is. All right, so we're going to start out with actually deriving this equation for psi using what's called the infinite square well in one dimension. So the square well is, imagine that you have a well that's infinitely deep. From an energy point of view, we have a potential here which is infinite at x equal to 0 and x equal to L. If the potential is, if you need an infinite amount of energy to get past it, you're not getting past it. That's the equation we're working with over there, or at least the one-dimensional version of that. So negative h bar squared over 2m, second derivative with respect to x. So we just need to come up with an equation that will satisfy that. And so, fortunately, it has been done already. But we're going to start out with just some generic A sine kr, kx, plus B cosine kx. Just a generic equation that I know that that will work. In the region where it can exist, my potential is 0. So this is the bottom of the well. Potential is 0 here. So in the region where this exists, that V is 0. So I end up with negative h bar squared over 2m d squared psi dx squared equals e times psi. I have some boundary conditions here, because this is a function with respect to x there. So at x is equal to 0, so psi of 0 is equal to, well, if x is 0, this goes away, so 0, plus b times, well, plus b, because cosine of 0 is 0. Sorry, cosine of 0 is 1. And I know that the wave function can't exist at this infinite boundary. It can exist just side of it, but it can't actually exist there, so that's equal to 0. So immediately we card out with the generic all-purpose equation and see that this term right here goes away, because that coefficient has to be 0 to satisfy the boundary condition. We have one other boundary condition. I know that psi when x is L is equal to 0, because again, the particle cannot exist at the wall. That is equal to A sine of KL. So from this, well, we can divide by A. We aren't identifying A yet, so we have to figure out when is sine of KL equal to 0. For what values of that will the sine be equal to 0? When is the sine equal to 0?
At 0.
And
1, 8, no.
okay, 0 pi,
2 pi,
etc. So at some value of pi, so in pi, where n is just an integer, n is an element of the integers. So we have now taken this into, so we started out with a general equation, we got rid of one of the terms, and so we now have it down to psi is equal to A sine of, well, k is going to be n pi over L times x, where n is just some integer. Well, we have to narrow this down some. But first, we have to, one, figure out what A is, not necessarily in this order, and two, figure out what the energy levels are. I know that using this equation right here, negative h bar squared 2m times the second derivative with respect to x of A sine of n pi over L times x equals E times psi. So let's do it. What is the second derivative of this with respect to x?
Negative.
The a in pi over L all squared. Sine of n pi over Lx.
Is equal to e times a sine n pi over L x. So if this is always true, then my coefficient of sine here and the coefficient of sine there have to be equal to each other. A can cancel out, and so I'm left with the negatives cancel out. So let's go for the typical stunning visual effects. And so I have negative h bar squared over 2m times n squared pi squared over L squared is equal to E. Or slightly different form, negative sign goes away. H bar squared pi squared over 2m L squared times n squared. If I treat this right here as sort of a base energy, if n is equal to 1, that's what the energy is equal to. So for n equals 1, let's just let E equal E sub 0. And so now the energy levels of the infinite square well will be E sub 0, and then if n is 2, for E sub 0, then 9 E sub 0 for n is equal to 3, 16 E sub 0 for n equals 4, and so on. So we now know the energy levels that can exist for this, but we don't quite have the equation yet because we don't know what A is. So this comes down to what exactly is psi? In the 1920s, I want to say, it's possibly early 30s, there was a meeting of the great minds of quantum physics. There's a picture of them with, pretty much the Nobel Prize winners of the time. The meeting was in Copenhagen, so this is called the Copenhagen interpretation. That if you take your wave function psi and square it, that is going to be equal to the probability of the location of the particle. I know at the simplest energy level, in other words, when n equals 1, if n is 0, there's no energy, so we're not talking about that. When n is equal to 1, my wave function looks like this. This is n equals 1. At n equals 2, it's going to look like that. N equals 3. These are all coming from our equation right here. If I square psi, then most likely the particle at the lowest energy level is going to exist smack dab in the middle. That's the most probable. There's some probability that it's going to exist anywhere in between, but it fades off pretty quickly once you get near the edges. In the second energy level, if I square that, the most probable places that the particle is going to exist are here and here. Not in the middle, not at the edges. In the third energy level, if you square that, I now have 4 places where I'm not expecting the particle to be at all, and then the most likely places that it will exist are going to be in one of those 3 spots. So if I actually want to figure out what A is, well, I know squaring it gives me a probability, and I know the probability that the particle is somewhere in here is 1. I'm basically going to square psi and integrate from 0 to L. And it's all going to work out beautifully. There won't be a single Keros error. So questions before we actually do a little bit of calculus here? So we have psi is equal to A sine of n pi over L times x. I'm going to integrate from 0 to L, because that's the range in which this wave function is defined. A squared sine squared n pi over Lx dx. And that's equal to 1. We can factor the a squared out, it's a constant. So a squared integral from 0 to L of sine squared n pi over Lx dx equals 1. So basically I'm going to solve this right here. And I know that times a squared is going to have to equal 1. And so once I have that, I can easily solve for a. All right, integral of sine squared. How do you do it? This is when you're supposed to respond back with how to do it. In case you got a little confusing.
Look it up.
Okay, then look it up. It's probably going to give you 2 in terms of a single thing there, so let's do a little u substitution while you're doing that. So let u equal n pi over Lx. du will be n pi over L dx. So we'd end up with a squared L over n pi integral from 0 to L, so from 0 to n pi sine squared u dv. Okay.
X over 2, or I guess u over 2, minus sine 2u divided by 4.
Minus sine 2u?
Divided by 4.
I assume the whole thing?
Yeah.
Okay. In terms of how you do it mathematically, and not the looking up method, which is fine in physics, but how would you do it the calculus way? I guess look it up. Just a quick side note. I know that cosine of 2x is equal to cosine squared x minus sine squared x. I know that cosine squared x plus sine squared x equals 1. So therefore cosine squared is equal to 1 minus sine squared. Plug that in, and so we end up with cosine of 2x equals 1 minus 2 sine squared x. Therefore, sine squared x is equal to 1/2 of 1 minus cosine 2x. Then you integrate that. So that's why you get a sine of 2x there and where the 1/2 comes from. Where that 1/2 comes from. All right, little plug and chug, plug in n pi, and so we have a squared L over n pi times n pi over 2 minus 0 minus, plug in n pi here. Well, that's just going to be 0. Because no, any multiple of pi sine is going to be 0. Plug 0 in and you get 0. So we end up with, that's equal to 1. N pi's cancel out. I'm left with a squared L over 2 equals 1. And so a squared is equal to 2 over L. A is the square root of 2 over L. So we now have a wave function that can describe this particle in a box. So psi is equal to the square root of 2 over L times the sine of n pi over L. So this is a basic approach. Is you're given the situation and then you try to find a function that works for it, apply boundary conditions, and solve. Infinite square well, or infinite 1D well, is the only thing that's simpler than that is the free particle. That's the one I decided to skip because that's I don't think there's as much benefit from that. Questions here? Let's do the harmonic oscillator.